All right, Honors Chem, we are going to talk about atomic theory today. We are going to talk brief history. So today is going to feel very much like a history day, history class. So here we go, atomic theory. Early years. So the early years were about 2,500 years ago. We're going to stop in ancient Greece, where most of Western history is thought to have originated. So the ancient ideas about matter from the ancient Greeks, we have two main competing ideas here. We have Democritus, he was probably better known for his idea of democracy. He's not really known as a scientific philosopher, but he should be more known for it. His idea of matter is that matter was composed of atoms which move through empty space. So we have atoms or empty space. Now, he used the word atomos, which in Greek means uncuttable. So his ideas of atoms were essentially a thought experiment. So let's think about this. If I had an apple and I took that apple and I cut it over and over and over again in half and in half again and in half and in half and kept cutting and cutting and cutting, eventually I would come to a small little piece of apple that is uncuttable. So that's the idea of atomos. Atomos means uncuttable, okay? He thought of atoms as solid, homogeneous, indestructible, and indivisible, hence the word atomos, uncuttable, indivisible. Different types of atoms had different sizes and shapes. So he thought, for example, that iron had hooks on it so that it could bend but still be solid. He thought that clay had like a ball and socket joint so that it could be flexible and squishy. Shape, size, and movement of atoms determined the properties of that matter. So he thought each type of thing had its own type of atom. Okay? And then about the same time, they overlapped each other. We have Aristotle. He actually stole this idea from a guy called Empedocles. So Aristotle and Empedocles said that empty space cannot exist. All matter is made out of four elements, four and four only. We have earth, fire, air, and water. Now, those of you who like anime might notice that those are the same four elements as The Last Airbender. So guess what? The Last Airbender is not that original. They're using Aristotelian theory for the four elements. Okay, so this is the idea behind Empedocles and Aristotle. We have fire, we have air, we have water, we have earth. So let's think about what they were able to observe back then in ancient Greece. We have a tree, right? And if we see a tree growing, we know that the tree has to have some earth to grow in. We also know that that tree has to have water in order to grow. Back then, I'm not sure that they knew that trees needed air. But if we chopped down that tree and we made wood, like a wood log off of that tree, and we burned that wood log with a fire, let's see, let's put a flame in there. Let's make that yellow in the middle. So we get a little bit of fire going. When we get that fire, if you've ever been next to a really hot fire, don't you get some little gusts of wind coming off that as heat? And you get ash coming off of that as well. And ash, doesn't ash kind of look like earth? And we start that whole cycle again with earth, water, wind, and fire. So that's what they were able to observe in ancient Greece. Now, Democritus's idea is really a thought experiment. Aristotle and Empedocles actually had evidence. This is what they said was going on. This was their evidence. So guess what? We always want evidence in scientific thought, don't we? So Aristotle's ideas won out, and they won out for over 2,000 years. So powerful were Aristotle's views that they dominated scientific theory until the beginning of the 17th century, 2,000 years. Okay, so we have our next guys. We have Sir Robert Boyle and Sir Isaac Newton. Now, both of them were at Cambridge, and they both published articles stating their belief in the atomic nature of elements. Now we're starting to hear atoms again, and they're bringing up Democritus's ideas again. Now, Sir Isaac Newton is mostly known for his theories of relativity of gravity, and his invention of calculus, so that we could observe physics with a mathematical model. But before that, Sir Isaac Newton was actually what we call an alchemist. An alchemist believed that we could take atoms of different elements and turn them into other atoms. So alchemists' goal were always to turn everything they could into gold. And when Sir Isaac Newton did this over and over and over, and he started to realize that, turning stuff into gold doesn't really work. So they didn't offer any proof. This is just Sir Robert Boyle and Sir Isaac Newton's idea. Then about 100 years later, about 100 years, we get a guy named Antoine Lavoisier. Now this guy was from France. He was an interesting guy. He was in Napoleon Bonaparte's cabinet. He was his scientific minister, or the minister of science. He married a very rich lady, and he used her money to do his experiments. One of the things that he did is he took solutions or different experiments, and he bottled them up and had the reaction happen. And then once the reaction was done, he weighed the bottle of that reaction. And he always saw that regardless of what the reaction was that he did, that the mass of the reactants, what we start with, equals the mass of the products, or what we end with. Okay? So for example, here in this reaction, we have this test tube here that is full of a sodium nitrate solution. And we've got a salt solution here on the bottom. And that salt solution, they're separate. Now, if I turn this over and let the sodium nitrate, or the silver nitrate, and the sodium chloride solution, or the salt solution mix, I will get a white precipitate, meaning a white fine powder will start to fall to the bottom, or solid will start to fall to the bottom. And that's because the silver and the chloride get together, and the sodium and the nitrate stay in solution. We definitely get a chemical reaction. We get a solid forming out of there, and we get a color change and all kinds of stuff going on. But notice that when we do this, the mass where we started is the mass at the end. So he came up with this very, very important idea here. He proposed that in ordinary chemical reactions, matter can be changed in many ways. Yeah, we created a white precipitate, but it cannot be created or destroyed. So I can change matter. I can get atoms to rearrange. I can get a reaction to happen, but I can't create or destroy the matter that I start with. What I start with in terms of mass and types of elements is what I end with. I've just rearranged what they're bonded to. So this is the biggest idea of Antoine Lavoisier. And it's a big idea that we use to this day. Okay? So here's an example. I've got 4 atoms of element A right here. Oh, I guess I can't color on that graphic. Or can I color on that graphic? Can I color on this graphic? Nope. I've got 8 atoms of element B. And when I make it, notice I have elements A and B. I've got elements A and B bound together. I still have 1, 2, 3, 4, 5, 6, 7, 8 of element B. And I still have 1, 2, 3, 4 of element A. They're rearranged. The mass is still going to be the same, though. I have a mass of 4 for A and a mass of 8 for B, mass of 4 for A and a mass of 8 for B, which will still add up to 12 total. Okay? So this is the theory that we use a lot in chemistry. Okay? Then about 50 years after Antoine Lavoisier, we come up with Dalton. Now, Dalton is an English Quaker. He was really, really good at reading other people's ideas and coming up with his own ideas and missing some really big ideas that people had in their papers, but they missed. So he was able to synthesize ideas really well. He wasn't super awesome in the lab. He did his own experiments and he fiddled around, but he was really good at seeing big picture ideas and putting them together from other people's work. So this is what he did. This is his main ideas. Matter is composed of extremely small particles called atoms. We have atoms again. Okay? So atoms are definitely something that we have again. Atoms are indivisible and they are indestructible. So I cannot break an atom. I cannot destroy an atom. In fact, he thought of atoms as this. He thought of them as round balls called billiard balls. Now, we don't really play what we say billiards in the United States. Billiards in the United States is called pool. So he thought of atoms as little tiny pool balls that are hard and indestructible. We can't cut them, we can't destroy them. Okay? Third idea, atoms of a given element are identical in size, mass, and chemical properties. So I can tell what I have based on its size and its mass, because anything that has the same size and the same mass is going to be the same element. If I have a different size or a different mass, it's going to be a different element. Okay, atoms of a specific element are different from those of another element. So what another way to say the same thing? Different atoms combine in simple whole number ratios to form compounds. So for example, if I have carbon dioxide, I have 1 carbon and I have 2 oxygens. Or if I have water, I have 2 hydrogens and I have 1 oxygen. I have simple whole number ratios when I'm making a compound. In a chemical reaction, atoms are separated, combined, or rearranged, but they are not destroyed. So he still used Antoine Lavoisier's idea of separation, combined, rearranged, but not being destroyed. So this is what we call the billiard ball theory of atomic theory. Okay? And about 50 years later, we come up with another British guy. We have J.J. Thomson, or Joseph John Thomson. He really goes by J.J. He did several experiments in the late 18th or the late 19th century. Notice his experiment was in 1897. So back in 1897, I don't know how much history you guys know, but in the 1890s, especially in the Niagara Valley of New York, This was Edison and Nikola Tesla's war of electricity. Everyone was trying to harness electricity. So you had Tesla and Edison fighting it out at Niagara Falls, trying to capture all that energy and generate it into electricity. You had Nikola Tesla and Gauss and all kinds of people just doing crazy experiments with electricity. Well, across the pond in England, J.J. Thomson was doing the same thing. He was doing lots of experiments with electricity. He was doing a cathode ray, and he used a cathode ray with a phosphorescent screen on the back so he could see the ray, and he noticed that he could deflect that ray with a magnet. And he noticed that the ray was deflected towards the positive side of the magnet. Now, we all know with electricity and magnets, opposites attract. So if it was attracted to the positive side of the magnet, what can we say about the charge of the electrical current going through that cathode ray? We can say that it was negative, okay? So J.J. Thomson was credited with the discovery of the first subatomic particle, and we call that an electron. Now, we symbolize electrons with a lowercase e and a negative sign in the upper right-hand corner like that. I will embed the cathode ray tube experiment so that you could see what it looks like. Okay. Then we have Robert Millikan. He obtained the first accurate measure of the electron's charge and also mass. With this, he found that the mass of an electron was calculated to be 1,837th of a hydrogen atom. This is the lightest known atom. Remember, they didn't think anything until J.J. Thomson came around was smaller than hydrogen. We just found something to be almost 2,000 times smaller than hydrogen, and it's an electron, okay? So Robert Millikan was actually able to do that. And look at that, 4 sig figs on there without the electronic balances and things, fancy equipment that we have here today. Pretty amazing stuff. And then again, Thomson, J.J. Thomson was a busy guy. So he knew that if there was an electron in there that was negative, by the way, he didn't call them electrons back in the day. He called them corpuscles, but we call them electrons. Thank goodness it's not called a corpuscle. If everything has electrons in them and the electrons are negatively charged, why don't we get shocked every time we touch stuff? J.J. Thomson realized that stuff was neutral. So if stuff was neutral and it had negatively charged particles in it, it also had to have positively charged particles in it. So he went on a hunt trying to find the positively charged particle. And he found that those positively charged particles have the same amount. Oh my goodness, what's going on here? They have the same amount of charge as the negatively charged particles. And these particles are called protons. Protons. And we symbolize protons with a lowercase p. And what is going on? I see Word doesn't want to respond. And a plus on the upper right-hand corner, okay? Thomson calculated the mass of a proton to be about 1,836 times that of an electron, or pretty much the same size as a hydrogen atom. Oh, I need to write. So as a hydrogen atom. So we now know that most of the mass of the atom, especially the hydrogen atom, comes from the proton. Very little of the mass of an atom comes from the electrons. So this is the atomic model that J.J. Thomson envisioned. He envisioned a positive matrix that is an even distribution of that positive charge. And embedded randomly within that matrix are the electrons. Okay? So, being the British guy that J.J. Thomson is, he thought of this as a pudding. Now, in England, a pudding is a cake. Notice we have little bits of fruit randomly distributed within that cake or that pudding. So he thought of this as the plum pudding model of the atom. We have that positive matrix, that is the cake part of the pudding, and then we have the random electrons are the bits of plum. Okay? This is a very common cake in Britain, especially around the Christmas holiday season. So if you have British heritage, you might have actually had some of this. All right. Our next guy is our one and only non-European guy. Now, he is definitely European in descent, though. We have Ernst Rutherford. He was born in New Zealand, so he was a Kiwi. All right. He's a Kiwi, just like our principal, Mr. Wahangi. He came to us from from New Zealand. When he first came to Cambridge, Ernst Rutherford was not very welcome in Cambridge because they didn't think that anyone who was non-British could actually have any scientific chops. And he proved them wrong pretty quickly. Within a couple of years of coming to Cambridge, Rutherford had a Nobel Prize. So I think most of the professors at Cambridge were eating humble pie at that point. Ernst Rutherford had a couple of really, really brilliant undergraduate people working under him. We have Hans Geiger, who is this guy right here, otherwise known as the guy who invented the Geiger counter for nuclear measuring. And we have Ernst Marsden right here. They subjected a very thin sheet of gold foil to a stream of positively charged subatomic particles, alpha particles. Okay? They knew it was radiation. They didn't really know what an alpha particle was, other than they knew that it was positively charged. They found that most of the particles could pass right through that gold sheet, which we would expect with a plum pudding model, right? Positive charge is going to go right through there and not be deflected by anything at all. From this, Rutherford concluded that the atom must consist mainly of empty space, which is not surprising, according to the plum pudding model. Rutherford, though, was pretty dang surprised when he saw that a few particles were deflected at very large angles. Okay, so when we had those particles deflecting at very large angles, in a sense ricocheting, that means there was something really heavy, really dense, and probably positively charged as well to get it to deflect like that. If you have a positive and a positive with magnets, they're going to deflect each other and ricochet. And that's what Rutherford was thinking. He's like, well, I've obviously got something that's very heavy, very dense, and positively charged to get this ricochet effect going on. He was quoted as saying that he was surprised as if a cannonball was being deflected by a piece of tissue paper. Rutherford later concluded that this must have been the result of a small core of positively charged particles. This is what he called the nucleus. Okay? So this is what Rutherford set out with his experiment. He had a lead block, and it was full of uranium. So in that lead block, he filled it with uranium. And he knew that the uranium gave off alpha particles. And by the way, an alpha particle is essentially a helium nucleus. It doesn't have any electrons, but it has a mass of 4 This is the mass on top, and it has 2 protons in it. And he shot these out through that gold foil, and he made that gold foil as thin as he possibly could. I think they measured it. They thought it was about 3 or 4 atoms thick. Okay. And they had this shield behind here. The shield was made of zinc sulfide. And the really cool thing about zinc sulfide is when it's hit by an alpha particle, it fluoresces or it glows a little bit. So you can see where those alpha particles are hitting. So they were expecting all of the alpha particles to be hit directly in the back. But they noticed that some of these alpha particles were being deflected, some at slight angles and some at really big angles. And they were like, what is going on? Especially these that were deflected at really big angles. What is going on to deflect these at really, really obtuse angles that are indicated of like a ricochet effect? They thought about this for 2 years. And so this is what they came up with. They came up with this idea of the electrons being around in the outside part of the atom and a small, very densely positively charged thing in the middle of an atom called the nucleus. So this is where our nuclear model of the atom first takes shape. And notice it takes shape just about 100, 120 years ago. It's really not that old of a model. Okay, so then we have another British guy about 1932. We're now within 100 years. He found high energy particles with no charge whatsoever. So when we had no charge whatsoever, it essentially had the same mass of a proton. And these are known as neutrons. Okay, why are we going here? So these no charge particles are called neutrons. And I want to erase that because that is not very good. Oh, it doesn't want me to write here. Let's write here. Neutrons. Okay? Now we symbolize neutrons with a lowercase n and a little 0 or a not symbol up on the upper right, showing that it does not have a charge. So just by the way, we have electrons, we have protons, and we have neutrons. So we have our 3 main subatomic particles. J.J. Thomson, again, he was working with what seemed to be 2 neon atoms, 2 different types of neon atoms. They were exactly alike chemically, but they were different in mass. Now remember, Dalton said that elements, if they were the same, had to be the same mass. But Thomson's finding that he's got neon, they act like neon, but they have different masses. Atoms of the same element that have different masses are called isotopes. Iso in Greek means same. Tope means type. Okay? So isotopes mean same type. Come on, erase. Okay? So isotopes have the same number of protons, but they have a different number of neutrons. All atoms have isotopes. All different elements have isotopes, okay? So there are 3 different isotopes of hydrogen, and I don't expect you to memorize all the isotopes of the different atoms, okay? The isotopes of hydrogens are named protium, pro means 1, deuterium means 2, and tritium means 3. So protium, because it means 1, it has 1 proton, it has 0 neutrons. It has a mass of 1. Okay, Notice our mass number is our number of protons plus our number of neutrons. Protons plus neutrons equals our mass number. Okay? Deuterium, do 2, right? 1 proton, 1 neutron, so we have a mass of 2. Tritium, tri, means 3. 1 proton, 2 neutrons with a mass of 3. Notice, and this is a huge point here, that our number of protons is always 1. So the number of protons IDs an element. So all atoms with 1 proton are always going to be hydrogen. Okay, they might be the different isotopes of hydrogen, but 1 proton means hydrogen. 2 protons is going to mean helium. Okay, so protons ID an element. Okay, so here we go. Atomic number. Atomic number is the number of protons. So when we look on the periodic table and we see an atomic number, that also gives us the number of protons in that element. Okay? Atomic mass is notice we have the average atomic mass. So I should put an average here. The average atomic mass is the weighted average of the relative abundance of the isotopes. Okay, so for example, if I wanted to take the average mass of all of you in my chemistry class, and I'd say I had 20 students that weighed 100 pounds, and I had 10 students that weighed 200 pounds, how would I take that average? Would I just add up 100 plus 200 and get an average of 150? No, I would have to take 20 times 100 because there's 20 students with a mass of 100. I would have to take 10 times 20 because there's 10 times 200 because there's 10 students with a mass of 200. Add that all up and then divide it by 30. So by that, I mean a weighted average. I have to take into account the relative abundance of the type of isotope that I have and make sure that isotope is counted in proportion to how it actually shows up in the world or the universe. Okay? Mass number is the sum of, so I'm going to use the Greek symbol. This Greek symbol is sum of, epsilon, protons plus neutrons. So the mass number is the sum of the protons plus the neutrons. Okay, so here we go. We've got 2 isotopes of copper. Notice they both have 29 protons, but one has a mass of 63. So we put a mass number on top, and one has a mass number of 65. So with this, we can figure out how many protons, neutrons, and electrons both of these isotopes have. So they both have 29 protons because remember, the proton number is the atomic number. So they both have 29 protons. And if they're a neutral atom, they're both going to have the same number of electrons as well. Okay? But the neutrons, now to find the neutrons, couldn't I take the mass number and subtract the proton number to find the neutron? So 63 minus 29 will give us 34. And 65 minus 29 will give us 36. Notice in the isotopes, the neutrons are different, but the protons are always the same. Okay? So that's how we do isotopes. Now, we're going to do this following graph really quick. So I have lead. I have the atomic number of 82. Now remember, atomic number gives us the number of protons. You're going to want a periodic table. So I'm going to grab a periodic table to help me with this. So we've got 82 protons because the atomic number is the number of protons. And if we have a neutral atom, it will also have electrons. Now, protons, this one has 8. So if I look at 8, on 8, I see, let's see, let's put this up here. On 8, I see that I have oxygen. So oxygen has the atomic number of 8, gives me 8 protons and 8 electrons. 30 electrons probably means it has 30 protons. If I look on zinc, zinc is 30. So that will give me zinc. I have 30 protons, 30 electrons, 30 is my atomic number. Okay? So just a little bit of what we have going on here. We have electrons. They are in the space surrounding the nucleus. We have a charge of -1, a relative mass of 1,837th, really, of a hydrogen atom. We have an actual mass of 10.11 to the -28 grams. Proton, it's in the nucleus. It has a relative charge of +1, a relative mass of 1. Its actual mass in grams. Neutron, I'm going to put these symbols here. It's also in the nucleus. It has a relative charge of 0. It has a relative mass of 1. Okay, so isotope abundance for element X. Let's do this. Let's figure out the average. Now we want to do a weighted average here. So we are going to calculate this weighted average. So I have mass of 6.015, and I have a relative abundance. Can I make that percentage a decimal point? If I do, I move the decimal 2 places over. So 0.0759. And then I need to add it to the other mass of the other isotope and its relative abundance in decimal form. And I'm going to add those up. So if I take 6.015 times 0.0759, I get, let's put this in another color. So for this part, I will get 0.4, let's see, I have 3 sig figs, 0.4565. That 5 is I'm gonna keep that there, and I'm going to circle that so that I know that I need to round before then. And the other one, 7.016 times 0.9241, I have 6.483. And I'm going to circle that so I know whether to round up or down. I'm going to add those up. I have 9, let's see, 5 plus 8 is 13, carry the 1, 9, and 6. So I have 4 digits that I can use. That 9 tells me to round up, and that 9 is going to tell me to round up as well. So I'm going to report this as 6.940 atomic mass units. Okay. AMUs, by the way, are atomic mass units. All right. So that is how you find a weighted average. Take the percentage in a decimal, take it and multiply it by the mass and add those all up. Make sure you pay attention to sig figs. Okay, we will do another average next time. We'll talk to you later. Bye.